Okay, we're ready. Go when you're ready.
Sure. All right. Yeah. Hey everyone. So last week I just talked about some background algebra, talking about rings and the Hilbert basis theorem. So this week I'm going to get into what pretty much makes up about the first half of my thesis, and so a lot of it will really be setting up the problem. So the title of the talk, or the series of talks, is From Analytic to um, Algebraic. So just to elaborate on what that's sort of talking about, so analytic will be talking about analytic functions, so functions whose Taylor series calculated anywhere converge, and analytic sets. Um, so those are the points which make either an analytic function or collection of analytic functions equal to zero. And so algebraic will be talking about polynomial functions, and um, algebraic sets. So, and those are the points in space which make either a polynomial or a collection of polynomials equal to zero. Um, so yeah, so my thesis is really about trying to take certain analytic functions and their zero sets, and if possible, replace them with polynomials, all sort of within the context of singular learning theory. And so, yeah, during this talk, I'll go through why that could be useful to be able to do that. So I'll just remind everyone of some of the stuff that Liam talked about last week, um, which sort of sets up the whole problem that we'll be looking at today. So, given a statistical model, and so that was a conditional probability distribution, um, which is parameterized by a weight called W. So at each value of a weight, you get a different conditional distribution between the input X and the output Y. And also given a true distribution, which is written as which is also a conditional distribution, which captures the correct relationship between the input and output. So given a model and true distribution, the Liam talked about last week how the free energy and in turn things like the generalization behavior of the model is determined by a constant that Liam introduced called the RLCT, or the real log canonical threshold. And so because of this, calculating lambda is one of the main ways you can try to understand a model. So more specifically, how you can understand how that model generalizes as it learns from new data. So I'll run through the sort of rough outline of how lambda is actually calculated. So lambda is calculated from the Quebec Labla divergence. So I think a couple weeks ago, Edmund introduced this quantity, but I'll just remind everyone what it is. So this function sort of measures the distance between the model P and the true distribution Q at each particular parameter. So it's this integral where you integrate over the input distribution and the true distribution, and then you have this logarithm. Okay, so, and also I remember Edmund a couple of weeks ago introduced strictly singular statistical models. That was defined through the Fisher information matrix being degenerate at some points, but for strictly singular models. This function k of w is often a complicated analytic function. And it has singularities in its zero set. So the set of points which make k of w equal to 0, which is also known as the set of true parameters. That set contains singularities. I won't go through the precise definition of a singularity, but I think that will be covered in future talks. So I'll just jump over to the next board. And so the RLCT lambda is calculated by resolving these singularities. So that's, I think, yeah, it's quite a vague description of the process, but I believe in Ken's talk later today, he'll be talking about resolutions of singularities, which should sort of clarify what I actually mean by that. But from what I understand, the rough idea is to try and find a coordinate transformation which sort of simplifies the form of the KL divergence. So the problem with this, and I guess one of the reasons that actually using singular learning theory or the techniques from it on actual models, one of the reasons it's quite difficult is that in general, this is hard. So this process of resolving singularities, it's based on, a lot of it comes from Hironaka's theorem on the resolution of singularities, which is a hard theorem to understand, and even in simple examples, the process can be quite difficult. So especially with just a arbitrary or just some analytic function that you're trying to resolve the singularities for. So in practice, people, including Watanabe, do something else. So instead, Watanabe and others who do singular learning theory calculations replace k of w by an equivalent polynomial. So instead of taking this analytic function k of w and directly computing the RCT for it, people generally first try to find a polynomial which sort of captures all the information needed to calculate the RLCT. So I'll talk about what I mean by equivalent specifically. So two non-negative analytic functions. So I'll call them h of w and k of w. So we call them equivalent if there's two positive constants, c1 and c2, such that you have the two following inequalities. So c1 times h is always less than or equal to k, which is always less than or equal to c2 times h. So for anyone who's taken a course in metric spaces, this is a similar idea to Lipschitz equivalent metrics or Lipschitz equivalent norms. And so the reason that we have this definition or care about this idea of equivalence is that if the two functions h and k are equivalent, then they have the same RLCT. So if you do want to calculate the RLCT for a model, you can do that by trying to find a simpler function than the KL divergence, which is equivalent to it, and then just calculate the RLCT using that function instead. So I won't prove this lemma here. So although this lemma is sort of used and stated by quite a lot of people, it's actually hard to find a proof of it. But I do know Tom Waring, who is one of Dan's master's students who's recently finished, has proven this lemma in his thesis, which so if you're interested, I think that's can be found on Dan's website. Okay, so then the question is, given a model, how can you find an equivalent polynomial? And so this is the question that my thesis has been looking at. So as I said that previously, in the literature, people like Watanabe often use this technique of replacing the KL divergence by a polynomial. The issue is that no one ever really justifies what they're doing, or they don't prove that it's equivalent, or sort of talk about the process of how they found that polynomial. Often people just state that a given polynomial is equivalent and just go on from there. So if you're trying to do your own calculations looking at different models, it can be very difficult knowing how to actually try and find one of these polynomials. So I'll go over to the next board and introduce the types of models which we'll be studying. So actually, Liam actually introduced these models last week, so I'll just remind everyone of what regression models are. So roughly a regression model is one which is constructed from a function, the function which takes an input and maps it to an output. So the model's conditional distribution is given by this exponential, which is sort of like a normal distribution based on the distance between the output y and the output of this function, which is called the regression function. And so that function is parameterized by the weight w. And so we also assume that the true distribution is given by the same type of model where the probability distribution is constructed from what we call the true function, which is just written by f with this subscript t. And so what the true function is meant to do is it's meant to take an input and correctly map it to an output. So for example, if the task was image classification, the true function would be a function which takes an image and always correctly identifies what's in that image. And so, so a couple of slides ago, I wrote out the definition of the Quebec Labla, of the expression for the Quebec Labla divergence. But when we're looking at regression models, the KL divergence becomes sort of much more easier to interpret. So if P and Q are given above, as above, then the KL divergence ends up being just the mean square error between the regression function and the true function. It's meant to be a minus sign in between those two. So that average is calculated with respect to the distribution which generates the inputs Q of x. So when the models are given in this form, the KL divergence really measures the sort of the distance between those two functions. So I also won't prove this lemma. I do know I do know that a proof can be found in Liam's thesis, which is also on Dan's website. So I guess, yeah, one of the reasons to be interested in regression models is that they include things like neural networks. And so Watanabe, in his book, he hints at a general method for taking regression models like this and finding an equivalent polynomial. So he states that in a remark, which I might actually go over to the next slide to write out. So what he calls remark 7.6. This remark states conditions which let you automatically, or according to the remark at least, let you automatically replace the KL divergence with a equivalent polynomial. So Watanabe states in this remark that if P and Q, so the model and true distribution, if they are regression models, and if you can write the difference between the two regression functions as a series of the following form. So if you can write it as a series where each term is a product of a function of w and a function of x, specifically where the functions of the weights, the fj's, are polynomials. And the ej's are linearly independent. So then if you can do this, Watanabe says, then by the Hilbert basis theorem, there exists some finite number j so that k of w, the Quebec-Labla divergence, is equivalent to this following polynomial. So it's just a finite sum of squares of some of the fj's, which come just directly from the series written above. So this remark looks quite useful. It says, okay, if you can write your model in this form, you directly get this equivalent polynomial. So the issue is that Watanabe doesn't actually prove this remark in his book or anywhere else, as far as we can tell. And so this has really been the starting point of my thesis. We started off trying to prove this remark, and as we went along, it realized it was actually quite difficult. And so there's, as far as we can tell, it doesn't hold in the generality stated here. And there's quite a few things that we're stuck on, but we have been able to make a little bit of progress, which has been what my thesis has been about so far. So I'll just introduce the setup for how we try to analyze this problem. So we define the Hilbert space capital L2, X and Q. So X being the input space for the variable little x, and Q being the input distribution Q of x. So we define this space as the set of functions on x which are square integrable with respect to the input distribution Q. So specifically, that's functions g such that if you integrate g of x squared multiplying by the input distribution, this is finite. So this is a Hilbert space which is equipped with an inner product. So that inner product is given by, so if you have two functions g and h, the inner product between those two is just you integrate them multiplied by each other and also against the input distribution Q. So I'm going to then go back to the first board. Okay, so from that inner product we get a norm. So given a function g, the norm squared of g, I'll just write out the space it's on, because there'll be a couple other norms which come up. So the norm of g squared is you integrate g squared against q of x. And so what this implies is that if P and Q are regression models, then if you remember the Quebec Labla divergence was just the mean square error between the two regression functions, then when viewing everything as happening in this Hilbert space, it means that the KL divergence is the norm of the difference between those two functions. Okay, so the starting point of us trying to understand this remark was, I guess, originally I think it seemed fairly reasonable, and perhaps even straightforward to prove. But over time, as we kept thinking about it, we realized it got harder and harder. But I'll outline just why it seems reasonable in the first place that it might be true. So firstly, to show equivalence between k of w and the polynomial that Watanabe wrote. So we need to show both an upper bound and a lower bound. So the upper bound being an expression of the form k of w being less than or equal to c1 times this finite sum of those polynomials, and the lower bound being a similar statement. So you have another constant times that polynomial. So if we had that the regression functions set aside the assumption, so specifically f of x w minus the true function. So if those could be written as this series of polynomials and linearly independent functions. If we assumed that these EJs weren't just linearly independent, but actually were orthonormal with respect to the inner product we introduced just before, then the lower bound would fall out almost immediately. So the reason that is that the KL divergence is, as we saw, was the norm between the regression function and the true function squared. And that's just the inner product of this difference with itself. And so just substituting in that series on both sides of the inner product. Then because the EJs are all orthonormal, so inner producting one with itself just gives you one, and when you inner product two different EJ of x's, you get 0. So this just equals the sum from j equals 0 to infinity of the fj of w's squared. So that's automatically larger than any finite sum. So if the EJs were orthonormal, the lower bound would fall out straight away. The issue is that in any actual examples of models, these EJ of x functions aren't orthonormal, and so this doesn't work. And it turns out that the lower bound is actually the much harder direction to prove, and that's one of the main things we're still stuck on. But we have been able to, I'll just go to the next board. We have been able to make some progress on the upper bounds. So I'll talk about what we've been able to find looking at those. So I think as I mentioned before, the Watanabe's remark 7.6, it's a very general statement and doesn't really have much conditions. So we've been able to find that if we add in a few extra conditions or things that we need to check, then we can prove that the upper bound actually works. So So I'll start by introducing the following lemma. So I'll just go through the argument to work out those conditions in a few different steps. But the first lemma is to suppose, so firstly, that the regression functions can be written in the series form that Watanabe introduced. Then the second condition is that if you consider the function tau, which goes from little l2 and r, so that's the set of sequences of real numbers which are square summable. So if you consider the function from that space to the Hilbert space we introduced before of functions, which is square integrable with respect to the input distribution Q. So this function takes a sequence of real numbers and maps it to the sum over all indices of those real numbers where you use them as coefficients to the EJ of x functions. So if this is well defined, so I should write if out the front. If this is well defined and bounded, so if anyone has taken Dan's metric and Hilbert course, they'll be familiar with the idea of bounded linear functions between norm spaces. But the rough idea is that the output, in some sense, shouldn't be any bigger than the input. So if that holds for that function tau, and lastly, if we look at these polynomials in the series at the top of the page, so the fj of w's, then for each value of w, you get an infinite sequence of real numbers. So if this sequence is in little L2 for all W in W, so meaning specifically that the sum of all j's of the fj of w's squared, if this is finite for each value of w, then we can conclude that there exists a constant c so that k of w is less than or equal to c times the infinite series of those polynomials all squared. So this upper bound that we obtain from this lemma still isn't quite a polynomial because it's so it's an infinite sum of polynomials. So after this lemma, we'll look at how we can try and turn that into a finite sum. So the proof of this lemma is fairly simple. It really just falls out of all the assumptions quite directly. So we have that the KL divergence, as we saw before, was the norm of the difference between the two regression functions, or more specifically the norm squared in that space. And so this series that we've got at the top here that is, if we look at it for a second, we can see that that's just tau applied to the sequence of, sorry, my drawing tablet's going a bit weird, the sequence of these polynomials. So this norm down the bottom equals the norm of tau applied to that sequence. And by the assumption that tau is bounded, that just means that there's this real number c, or positive real number c. So this is less than or equal to c times the norm of a sequence of polynomials, where this sequence is, where this norm is the little L2 norm. And specifically, that just equals c times the sum over all the polynomials squared, which completes that lemma. So if we look at the three conditions that this lemma requires, I think the third one looks fairly straightforward to check. It's just checking the convergence of a series. I guess the first one's a bit weird, actually knowing what models can be written like this, but we won't go into that today. But the second condition, I think, looks the most, at least the hardest to check at first. So it looks sort of confusing to actually understand this map. But I'll go to the next board and just introduce a condition which guarantees that that function tau is well-defined and bounded. So we have a lemma that tau is well-defined. I should say by well-defined, I mean that the output of tau, the function that it outputs actually is a square integrable function. So it's well-defined and bounded if the following series converges. So if you sum from j equals 0 to infinity of the norms of all the linearly independent ej of x functions, if you take their norm in the Hilbert space we introduced and square them and sum over them all, if this series converges, then tau is automatically well-defined and bounded. I won't prove this lemma just to save a bit of time, but it's actually not too difficult to show. I think from what I remember, it just involves using the Cauchy-Schwarz inequality.
I think you didn't finish writing the statement of the lemma.
I think it is. So the map tau is well-defined and bounded if this series is...
Yep, okay, yep.
Okay, so I mean, so far where we've got to is we've got that k of w. We've been able to show when k of w is bounded by this infinite series of polynomials. But as we require a polynomial in the end, we want to be able to replace that with just a finite sum of those polynomials. And so in the statement of the remark, Watanabe talked about the Hilbert basis theorem. That is, yeah, the main tool that we'll use to try and write bound by a finite sum. So I'll just remind everyone, so last week when I talked about the Hilbert basis theorem, so what that theorem says is that every ideal in a polynomial ring is finitely generated. So for us, we have a sequence of, we have an infinite sequence of polynomials. And so what the Hilbert basis theorem says that the ideal generated by all of those infinitely many polynomials is equal to the ideal generated by some finite number of them. And so specifically, for all indices little j, there exists polynomials which we write as using, denote using a. So aj0, aj1 of w, all the way up to the final index in the finite generating set, so capital J. So there exists a collection of polynomials so that the little jth polynomial can be written as a sum of these a polynomials and the generating polynomials. So specifically, you can write fj of w as a little j0 of w times f0 of w plus a little j1 of w, f1 of w, all the way up to the last generating polynomial. Okay, so I'll move over to the next bullet again and continue this argument.
Probably you said this already, but this step of reducing from infinite to finite is the principal reason we want these coefficient functions fj to be polynomial, right? Because the Hilbert basis theorem certainly doesn't work if you just have analytic functions.
True, yeah. That's a good point. Yeah. Okay, so using these expressions, we have this infinite series of the squares of those polynomials. But using those, we can plug those expressions directly in, and that gives us the following series. So f0 of w and then the last polynomial in the generating set. And so that's all squared. But so what you can notice is that this, the expression, each term of the series can be written as a dot product between two vectors. So specifically, we can put the all the a polynomials in one vector. And dot product it with all the f polynomials. And that gives us out that expression above. But what this lets us use is the Cauchy-Schwarz inequality, which tells us that the norm of the dot product is smaller than the product of the norms of each individual vector, I guess with some squares in there. So specifically, that means this series is less than or equal to the series where each term is instead the sum of the AJs squared multiplied by the sum over that generating set of polynomials, each squared. So immediately we can take this factor and pull it out the front. So that equals the sum from k equals 0 to j fk of w squared times then this series on the right. So you could write that as a j0 squared plus right up to a j w squared. So then if this series on the right, and this is a big if, and
Sum to infinity there, right? Quite
that's a good
important.
point. Yes. Yeah, so that's an infinite series on the right. But if it happens to be that this series not only converges for each value of w, but happens to be bounded by some constant at that works for all values of the weight w, then you get an upper bound by a finite polynomial, specifically the polynomial that Watanabe stated in his remark. And so showing that this series outlined in green converges is, I think, probably the hardest part of the calculation to actually check. But as we'll see in the next couple of weeks, there are certain models where we can do a direct calculation and show that it does converges, and show that a upper bound actually works. So I'll just go back to the first slide to conclude everything. I'll just write out a list of guarantee that the polynomial upper bound on the KL divergence works. So to conclude, firstly we have the condition from Watanabe's remark that the difference between the regression functions can be written as that series. The second condition, the condition was that linear function tau is well defined and bounded, but then in the previous lemma we saw something which guarantees that, so specifically the series of the norms of those linearly independent each of x functions. If that series converges, that guarantees that tau is well defined and bounded. The third condition being that at each value of w, the sequence of polynomials is in the sequence space little L2. And then the fourth condition, which is the most difficult to actually check, is that for each k equals 0 up to j, so this k index runs over the generating set of polynomials that we got from the Hilbert basis theorem. So if for each of those values of k, the series of those quotients, we square them all. If that is less than infinity, but more specifically, if that's less than some constant c for all values of w, then we can conclude that the KL divergence for those regression models is less than or equal to c times this polynomial. Yeah, and so I think, as I mentioned earlier, showing this fourth condition is quite tricky, and so that checking that condition on a few different models so far has made up the rest of my thesis, and going through some of the simpler calculations will be what the next couple of talks I'll be doing will be about. But yeah, so that I'm going to wrap up there. But if anyone had any questions about that stuff, yeah, feel free to ask.
Yeah, thanks a lot. Questions? So I guess it's. Oh, go ahead.
Oh, go ahead.
No, it's just going to say that as far as we can tell, maybe there's some idea for how remark 7.6 might be proven, obliquely mentioned in some paper, perhaps, but it does seem to be, after exhaustively looking through the literature, I think Spencer has, well, maybe there's still a few Watanabe papers you haven't read, but
there's still a few. I think I got to around maybe 2001 or 2002 before I swapped over to just writing a draft of my thesis. So there's still, I think, quite a few papers I should still get back to. But so
you mean
far,
going back further in time?
Yes.
Before 2001? I see. Watanabe, as far as I understand, had a couple of papers from 1999, but not a lot before that in relation to singular learning theory. So he was doing some work related to neural networks, but I don't think it was as theoretical. There are probably only a handful of papers, only maybe like a couple before 2001.
So I started at around the start and sort of saw quite a few of those papers. And it was sort of interesting seeing how over time he developed the whole singular learning theory thing. So, I mean, the issue I found with Watanabe's papers is he publishes lots of very similar papers. And so and occasionally there's like a little bit that's different in each one, and so it's always tricky sort of scouring through them, trying to find whether something's in there.
What about, so you said an exhaustive search through that literature, but you're just talking about Watanabe's literature. So what about the more general literature in algebraic geometry?
So I haven't actually looked at any algebraic geometry papers. I have looked at some papers by people who often collaborate with Watanabe. So, for example, Aoyagi has a few papers with Watanabe on calculating LCTs. And so she does a similar thing to Watanabe, where she often just says, here's an equivalent polynomial, and references this quite vague previous lemma by Watanabe to justify it. So it's still quite unclear how they actually know about it. Yeah.
So it is actually attributed to Watanabe rather than just to folk knowledge in algebraic geometry. Is that right?
Yes. Yeah. But so far we haven't understood what Watanabe meant in the things that's been referenced.
Yeah, from the point of view of algebraic geometry, it's a bit of an unusual combination of topics, right? One isn't usually constructing bounds on things, first of all. Secondly, the role of these Hilbert spaces. Of course, there's a lot of analysis in algebraic geometry, but there are some related ideas in analytic geometry that Edmund's been looking at, but they don't seem to fill this gap. At least we haven't figured out how. Maybe Spencer, if I could just ask you to. So why focus on this somewhat technical remark in Watanabe? Maybe it's something that's not proven, but why care about it? What's the?
Yeah. So I guess
significant.
So it's useful, significant, at least in my view, because if you actually want to go about calculating an RLCT of a model, which it seems like you really do need to try and replace the KL divergence by a polynomial. I guess also firstly, this remark seems to be a pretty general way of doing that. I think that's the main reason I think it's significant. It, I guess, also does let you bring, then if you can do that or something like that, it does let you bring in a whole lot more tools from algebraic geometry to study problems.
Right. I would say at a conceptual level, it's without this remark, it's actually hard to justify the title of his book.
Right, yeah.
Which is algebraic geometry and statistical learning theory, not analytical geometry, or analytic geometry rather. So without this reduction via the Hilbert basis theorem to a polynomial, it's hard to say it's a fundamental connection between learning and algebraic geometry per se. So I think it's quite important.
Does it affect the soundness of the rest of the theory, or is it just a glimmer of hope that it might be easier than the fully general case to calculate these RLCTs?
So as far as I can tell, I don't think it affects the soundness of the theory, but it is definitely important if you want to do any actual calculations.
Yeah. So yeah. Would I be right to say something like, if this remark turned out to be false or turned out not to apply for a specific model, then that wouldn't affect what geometry has to say about the model, but it would affect how practical it was to calculate the RLCT.
I think that's correct. Yeah, Dan, did you have any opinion on that?
Yeah, I think in some sense, you could say it's a practical thing where, because of the ability to introduce a polynomial, you can at least in principle put it on the computer and do calculations and maybe have some chance of computing the RLCT, even if it's difficult.
Yeah.
But I think it's kind of deeper than that. I mean, the structure of the theory is, well, Watanabe's theory would already be interesting and important if it stopped exactly where it is. Right? If that was it and it never goes any further, it's already very useful and interesting, I think. But part of the allure of the theory is the idea that maybe many more tools from one of the oldest and most developed parts of mathematics could be brought to bear on learning theory. And if the bridge between learning theory and algebraic geometry is like this ad hoc thing that you sort of get to work because you're lucky or clever in particular examples, which absent remark 7.6 is what we have, right? In particular examples, you can introduce this equivalent polynomial, but it's a technique that works on a per example basis. Absent, I mean, there's actually no general argument that you can find an equivalent polynomial, right? And absent a general argument like that, it's, well, how do you know you'll just keep getting lucky? Maybe what he's getting at in remark 7.6 is true, but that belief is kind of what could be wishful thinking, right? I don't know. So I think
it's quite interesting.